Okay, let's get started. Okay, still very good to see some of you are still here. So when I saw the email yesterday, I got confused because it says campus will be closed, right? And then in the later part of the email, it says, okay, and it will resume at 12:30. So kind of very confusing, and I'm almost didn't come today. Okay, great. Yeah. Let's have a brief review of our last lecture. So before that, so any questions, comments? So for the last session, who were in the last session yesterday? Oh, yeah, big. Yeah, we need to say sorry a little bit, right? So we don't have access code, and it turns out that so normally the access code would be granted to the TA automatically, but this time, the TA was kind of late. So he's still official TA now, but I think it's kind of late. He didn't receive the code. So I was asking for the code this morning, and I'll see how that will look like. Okay, very good. So let's do, when I traveled last week, so I got sick immediately in Utah. So by the way, here almost as cold as Utah. So yeah, and I didn't do the recording, so we'll continue lecture 3 today, and then I will find some time to add one more lecture. Okay, so yeah, here's a brief review of our last lecture, which is lecture 2. So in lecture 2, we covered these 3 bullets, right? The first one is the wavelengths of the sinusoid, and then we cover the effect of surfaces on propagation. Okay, and then we talk about antennas and the propagation. So let's see a little bit details very quickly here. So before talking about the wavelengths of the sinusoid, so we cover some concepts here, right? So one is this is speed of light is 3 times 10 to the power 8 meters per second. And then we cover some SI unit prefixes and like kilo, mega, giga, tera, right? So we're going to use, probably we don't use tera very much, but we're going to use these 3 very frequently. So just remember to remember them, okay? And okay. Yeah, and then you can see some examples here from Wi-Fi. Okay, and we didn't talk about this very much, but who heard of this? Voyager. So who heard of Voyager? Probably 2. Right, so a very cool spaceship, go to Saturn or Mars or whatever, right? So, if you're interested, you can take a look at this website, right? So, it's very cool, and then we can communicate with that, which is pretty amazing. And so here is wavelengths of the sinusoid. So basically, we start from a distance of 0, right? So, and remember that, so we have an angular frequency called omega, so that equals to 2 pi times f, where f is just the normal frequency in hertz, okay? And hertz is 1 over a second. All right, so in order to see the length of the wavelengths of sinusoid, so basically we're going to do some delay here. So, right, we do a delay of L, right? And then, since the wave will propagate in the speed of light, and then the distance will equal to c times the speed of light times the delay. Okay. In this case, we can compute the delay as c over c, right? And then we plug the delay b here, so we get it. Okay. And in order to see the wavelength basically that is the length of one period, right? We just let this term equal to 2 pi, which is the period of time. Okay. And then we can get this formula. Right, we can get this formula, and from here we can compute the wavelength, so which is lambda, right? So just remember this b by lambda, so that equals to c over f, right? So that's pretty important, right? So we need to remember this, and okay, and here are some examples for the cellular network, and so this is the wavelength, and for MRU, and this is wavelength. You can see that is pretty large, right? So one immediate use of wavelengths is to design, the distance between 2 antennas for a multiple antenna system. So we need to make sure that, oh, by the way, do you know why we use a multiple antenna system? It's not a single antenna.
To increase gain in a certain direction. You can increase the gain and the directionality.
Yeah, very good. Yeah, very good. Yeah, so basically, I think, yeah, what do you mean by increase the, yeah, I cannot say that exactly, but I think what you're saying definitely makes a lot of sense, but it's a little bit vague, right? So one reason we use multiple antenna is to increase the throughput of the network, right? Let's say, for example, what if antenna are totally independent and there's no interference? And for one antenna, we can transmit one data stream, another antenna can transmit another data stream, and so on. That would be great, right? So that is more or less happening in practice, okay, for the cellular system, right? But the condition why it can happen is that we need to put the antenna far apart of each other. Otherwise, it cannot be the same, okay? And this distance is determined by the wavelength. It should be like half of the wavelength, okay? The distance between the antennas, okay? More or less, right? Roughly speaking, it's not exactly like that, but that's basically the idea, right? So wavelength is a very important concept. Okay, and next we talk about propagation. So passes. So what if the signal, hits some surfaces, right? So we have three cases. One is reflection. So, oh, by the way, did you watch the video of lecture 2? Yeah, probably you did, right? So you okay? Okay. Yeah. So normally in the video, I do some cutting about my cough. So if you see, some kind of unnatural transition, so that's what I call. So, okay, great. Yeah, for reflection, basically once the signal hits a smooth surface, so it can reflect, right? And so basically it means that the features of the surface is large enough compared to the wavelength. And in contrary, so basically the scattering is the exact opposite. So basically, if the surface is rough, then the signal will come to everywhere, right? That's called scattering, right? That's when the feature of the surface is smaller compared to the wavelengths. And then we have diffraction. So that basically means that when the signal hits some sharp object, and then it can kind of pass through it a little bit, right? So that's called diffraction. Okay, but those are just all the concepts, right? It's not mathematical. Okay, and then we are trying to answer these two questions, right? So, how does the received power vary with the distance, and how does the received power vary with the frequency? Okay, and then we introduce this isotropic radiator model, right? And then we can see, so this is basically the received power density. It means that if I have a unit area of the receiver, then this is the power that we receive. Okay, and you can see, so if we have an iso radiator, so that is an isotropic radiator, it's short for that. Okay, and if you have an iso radiator, we can consider that the gain of the transmitted gain of the antenna is just 1. Okay, because we have nothing there. Okay, and then I think we introduce the transmit gain, which is GT, and then receive gain, which is GR, right? Yeah, and for the receiver, so basically we need to use the density multiply the area of the receiver, right? AB is 1, so that's what we see before. And if it's not 1, then we need to define it. So for practical antenna system, the area is replaced by the effective aperture called AE, right? So for dish antenna, so it looks like this. So basically, AE is proportional to the area of the dish. Okay, usually it's 50 to 70%. And for the tuned antennas, so basically AE can be computed in this way. So this is what we introduce in class, right? So that's the function of the received gain and also the wavelengths, right? And then if we plug everything in, so we can get this formula. So this formula is one of the most important formula, okay, in the first few lectures, right? So this received power equals to this thing, right? The transmit power times transmit gain, received gain, then wavelength square and divided by this, right? Okay, and so this method is very important. Just try to remember that. This is called free space equation. Okay, and from this formula, and we can see that. So here is basically lambda. So lambda equals C over F. So therefore, we can consider F squared would be in the downstairs, right? So it's the received power is inversely proportional to the distance square and inversely proportional to the frequency square. Okay, and that's the answer of our two questions we asked before, right? So those two are the relationship between the received power and the distance and the frequency. Okay, and that's everything we covered in the last class. Okay, any questions so far? on the next lecture. Okay? So today, we have 3 topics. The first is to talk about decibel, the dB notation. And secondly, we're going to talk about communication loss. Okay, which is definitely related to the received power that we receive, right? So from there we can see we lose some power basically for communication. And then we'll go back to the decibel notation. In particular, we'll talk about some decibel notation for power specifically. Okay, yeah, because power is normally important, right? Who heard of dBm, dBw before? Okay, very good, right? So that's basically unit we use in practice. Okay, and those are the topics today. And first of all, let's see the first one. So what is the decibel notation? So decibel notation basically is a log scale, right? For example, we say if we have a gain, we use a gain dB. So decibel is basically just dB, right? It's short for decibel. We have a gain. And the definition of that is 10 times log 10 of G, where G is a linear unit, right? So this basically is the definition of the decibel notation. So can you tell me why we need this kind of notation for this kind of unit? Yeah, basically we take a log, right? And what's the benefit of it? Right, why I want to take a log, right? So before we have this linear notation, right? For example, if it's gt and then it will be gt, right? So why would we take a log? Have this, yes?
Just to reduce the number, basically. So if you wanted to explain something in order of magnitude, then it's a lot easier.
Very good, very good. Yeah, that's one of the reasons. Yeah.
Instead of multiplying quantities, you can add them.
Yes, that's another reason. Very good, right? Computational-wise can be easier because we're just, instead of multiplication, we have addition. And the other reason is that what you said. What's your name?
Matthew.
Matthew, what's your name?
Eric.
Eric, okay, great. Actually, no, it's very funny. So the guy asked for the access code. It's called Eric. Okay, not you, right? Not me. Okay, so basically, when the G is very large, like 10 to the power of 12, right? It's a huge number, right? I don't want to write that, right? If you use this notation, the number will be much smaller, and it looks much more smaller, right? And on the other extreme, right? What if the number is super small, right? Like 0.00 whatever, right? If you use this notation, so the number is much more manageable from the visual, right? So that's the reason why we use that notation. I will not write it down, but motivation is that we avoid large and small numbers. Okay, and the other reason is that computation-wise it might be much easier. Okay, in industry we always use dB notation, so we almost never use linear, right? So we have heard, okay, so this is the transmit power, and it's definitely in dB something, right? It may not be in dB exactly, but in dBm, dBw, and so on. Okay, so this is the notation. Okay, so I did dB, and people turn it back, right? The G will be nothing but 10 to the power of dGB divided by 10, right? So this is dB notation, and this is a linear notation. Okay. Yeah, convert something from linear to dB, and convert it back from dB to linear, right? So this is kind of important. Okay. And now we understand what the decibel notation is, and given that, let's see some very common decibel, right? Let's see if we have some values, and let's say here is the linear, and here is the dB. So this is approximately, right? Not exactly, but this is what we use in industry all the time, right? I say for the linear notation, I say if we have 2, then 1 dB. Very good. Yeah, so clearly you're so familiar with that, right? 2 is very typical, right? It's like a double, right? Double means we add more, 3 dB more, okay? And how about 5? Right, this is not extremely common. Still know that? Yeah, it's not that common, but it's 7 dB. Another very common is 10, right? 10 is 10 dB, right? So we have to do it from here very quickly, 10 dB, okay? So I think 2 out of 10, so they are extremely commonly used. Yeah, any questions so far? So far so good, right? Okay, so now let's see. So let's get to the next step, right? So normally when we talk about antenna gain specifically, we don't use dB, right, directly. So we use something related. So normally what we do is that we have some typical antenna gain. Right? Let's say, for example, the ISO radiator. So what is the transmitting gain for that? 1, right? So normally when we design antenna, we want to compare our antenna gain to ISO radiator or for some other typical used antenna in practice. Okay, so this is what we do in practice. Yeah, let me write down the definitions. So basically, in practice, the antenna gains are given in dB, but so this is respect to ISO radiator or respect to another very commonly used antenna called half wave dipole. Okay, so when you compare the gains to the ISO radiator, it's called dBi, and when we compare the gains to the half wave dipole, it's called dBd. Okay, dBn and dBd. Okay, so now I see some examples. So basically, this is nothing but we just compare our GT divided by the GT of ISO radiator for the half wave dipole. Okay, and then this number would be in dBi or dBd. That's clear? Yeah. So I'll now copy the example. So let's show it. Oh, by the way, so for the half wave dipole, so basically that's a type of antenna that I don't know that exactly, but I think the antenna element is like half of the wavelength. Okay, that's the size. Okay, or some distance, right? So it has to do with wavelengths. Okay. And here you can see that clearly, if you consider the dipole, half wave dipole, then compared with its own, it will be 0 dB, right? Because it has to be divided by its own dB, which is 1. 1 is 0 dB, right? And then compare that and the ISO radiator, so it's 2.15. Basically means that it has a better gain compared to 1, right? So yeah, and also you can see there are other kind of antennas that we use, and here are the gains for dBi, and here are the gains for dBd. Okay. So is that clear? Right, so that's an example to show what the gains look like. And here we have an important bullet. So basically, all this dB, dBi, dBd, so those are not like real units. It's not like meters or seconds or so. So they're unitless. Okay, so we don't have units for that. Remember. So basically, you cannot in practice you cannot say, okay, so I transfer the power with 3 dB. So no. So dB is unitless. I can only say, okay, I'm better compared to you for 3 dB. Okay, and that's okay, right? So like we only use dB to compare stuff. Does that make sense? So questions? Good. Okay, so now let's turn it off. Okay. Now let's see a simple example. So what this block here? No. Yeah, maybe. I'll write it here. Can I see an example? So we consider the transmitted antenna. Gain from DSS 43. So DSS is some space station 43. Okay, so it's a base station in X band. So X band is nothing but frequency band we use for space communication. I think it's around 10 gigahertz. Okay, and if you look at all the band, each of them have a name, C band or whatever, you know. So CBRS band. So this is it's called X band. I think it's around 10 gigahertz for space communication. Okay, and this is for the Voyager 2. Okay, spacecraft. Oh, by the way, did you see any photos from Voyager 2 from NASA? Nobody have seen that before? Okay. Yeah, even now you should take a look at that. It's very, very cool. You know, I think I take lots of pictures from Saturn, and also some other planets. Okay. Okay, so the transient gain of that is 62.1 dBi. Okay, careful, so it's dBi. Okay. And now our question is to determine the gain GT in linear units. Okay, so what we give in dBi, then we need to determine that in linear unit. So what is GT equals to? And how can I solve this problem? Yeah, let's remember. So basically, we want to use something like this, right? Because this is how to convert from dB to linear, right? And the only thing we need to take care of is this dBi. Will it matters or not, right? So basically, so now we have, so this value is in dBi, right? So dBi basically means the ratio between this antenna and the ISO radiator, right? And the ISO radiator gain is 1, so it doesn't matter, right? Then we can use this formula directly to solve for that. Does that make sense? Okay, so if yes, yeah, let's just do it. So basically that is equal to 10 to the power of this guy, 62.1 divided by 10. Right, just use that formula exactly because GT for ISO radiator is 1. Okay, and so that equals to 10 to the power of 6.21. So roughly speaking, that is like 1.6 times 10 to the power of 6. Right. So those are all approximately equal, right? Yeah, you know what I mean. So we don't normally let's say write approximately everywhere. We just say equal. But this is not exact number. Okay. And so this is a linear gain. You can see it's a huge gain for this antenna. Okay. Almost like more than a million times. Okay. Questions? Pretty straightforward. Okay. Okay, so yeah, this is our first topic. Now let's see our second topic. The second topic is communication loss. Okay, so basically the meaning of the communication loss is the ratio between the transmit power and the receive power. Right, then that's a loss. Right, that makes sense? Okay, so let's write it down. So the communication loss, this is nothing but the signal attenuation. As a positive, the signal attenuation as a positive positive quality in dB. So basically, it defines like this: PLdB equals to 10 to the power of log 10 PT over PR. Okay, so that's basically the definition. Okay, so now let's see how this looks exactly, right? So hopefully you still remember, so what is the relationship between PT and PR, right? So did you remember it? Yeah, the formula we just mentioned, let's maybe write it here, okay? So let's say PR as a function of D, so that equals to what? Who still remember it? Yeah, just review that, right? So let's write that in terms of the effective aperture. In other words, write that as a function of the lambda. Right, so that's basically the PT times GT, the gain, the transmit gain, times GR, right, the receive gain, right, and then we have a lambda square, and on the downstairs is 4 pi distance square, right? So remember this formula? Yeah, we're going to use this many times in this lecture, okay? Can you remember that? Okay, so we can express the communication loss in two ways. So one way is with the antenna gains, okay? But since the antenna gain is kind of additional design of the antenna system, right? It's not a property of the channel, right? So basically, normally we model communication loss as a property of the communication channel, right? So basically, sometimes we consider that without GT and GR. Okay, so that's a two-way of consideration for the communication loss. Okay, so let's write both of them. So the first case is that with the antenna gain, this PLdB equals to nothing but minus 10 log 10 GT GR lambda squared for pi d squared, right? So it's PT divided by PR. So here we write PR in the downstairs, so we have a minus sign in front, right? So yeah, that's the communication loss with the consideration of antenna gain. And second case is that, so that is more interesting and probably we use that more in practice. So without antenna gains, right, then in this case, the PLdB equals to minus 10 log 10, and then this is lambda squared for pi d squared, right? So that's without the antenna gains, okay? And this is kind of interesting, right? Because those parameters, everything is given by the channel, So let's do some simplification for that. Okay, so the first of all, we can see we have a square here, we have a square here, right? We have a square everywhere, then we can take this 2 in front of the log, right? So we have minus 20 log 10 lambda over 4 pi d, right? Does that make sense? Questions? No? Okay, great. Can you see that? A little bit. Okay, yeah, oh boy. Yeah, after that I may write more on the other side. Okay. How about you? Can you see the other side?
Yeah, for the most part.
For the most. Yeah.
Some things are sometimes a little hard to see, but I don't
Yeah.
know.
Okay. So if you cannot see, just let me know. So I may use middle part more. So. Okay. Yeah. Yeah. Let me finish this revision and then we're gonna move to the other side. Or maybe we just move now. And because this derivation is pretty important, so let's derive it here. So here, okay? Good.
Yeah.
Yeah, I'll use this and that probably the most part.
When you write on that board, we can see it as long as you write on like the top half, because then the computer blocks the bottom
Oh,
half.
man.
So I don't know, I'll probably just move next to us.
Yeah. Yeah, maybe just try to, sit in the middle, right?
Yeah.
So it should be having enough space. You can move now if you want.
Yeah, it's just I need the outlet right now.
Oh, I see. So, yeah, this is what I normally do. I just write things here. I think you will better follow in this case, right? So, but if any of you or most of you prefer me to just use slide to go over it, it's also okay. Okay. But at this moment, I'll just do this, unless you tell me not to do this. Yeah, for me as a student, when I just read the slides in class, so I cannot follow exactly because there's so much more content in the slides. Okay, anyway, yeah, let's rederive it. So basically, without a 10 again. Okay, the communication loss equals to this. Then, this is what we got. 4 pi d. Okay? And then because this is the division, we can separate this, right? And the other thing is that we know lambda equals to C over F. Right? So let's plug let's plug this in. Yeah, because in practice, the distance and the frequency are pretty much what we use most. Right? So we plug lambda in here, so we get C over 4 pi df. Right? And then what we got is that, so we can take this df out first, right? Because those are kind of the channel parameter. So basically, because it's in the downstairs, and you can take that out, then we don't have this negative sign anymore. It's 20 log 10 df, right? And then we minus 20 log 10 c over 4 pi. Right, and from here we can see that. So we can break this too, right? Because it's multiplication. So we have 20 log 10d plus 20 log 10f minus 20 log 10 c over 4 pi. Okay, and this is almost the final formula, except this part, right? So we can see c is a constant, 4 pi is a constant. So that's basically nothing but a constant. Right? Okay, and then, so it, because it's constant, then we can compute it. So that is 147.6 dB. Okay, so we replace this number, we replace this by this number. Okay? And this is the final formula, right? So basically, our communication loss equals to this. And we can see that, right, if we have a bigger distance, then will have more loss, and if you have a higher frequency, will have more loss, right? Remember, this is a far field model, right? If it's near field, basically means the transmitter and receiver are very near, then this formula will not. It's only for far enough. Okay. Yes.
Is there like a typical variable that represents that constant, like a C or just a letter or something?
Okay.
Is there like a typical variable that represents that constant, like a Greek letter or a...
Oh, that's probably no. Yeah, just this number. So this is normally what we write there all the time. Yeah. So I can double check. Okay, so so there's one more comment here. So basically, for the 2 on the denominator, d squared, so that comes from the free space model. Okay, the reason I have 2 is because the area of the sphere has a d squared, right? That's why we have a 2 there, right? But in practice, antenna, so this 2 may not hold all the time. So we may have a greater loss. Okay, 2 is the best case we can imagine, right? Because that's the ideal, that's the theoretic, right? But in practice, so this number, the path loss on the D can be bigger than 2. Okay, so we call that, this is 1 over 4 pi d squared. So this square, so this is from the sphere area, right? This square, so that's called path loss exponent, right? What's path loss? Because that's a function of the distance. Okay. Yes.
Just, you put the 4 pi d within the square over there. Is that, does the 4 pi also have a square, or is it just a d?
No. Yeah, so, yeah, I need to be more clear. Yes, or that. So for the other 4 pi here, so that's come from the effective aperture.
Okay.
Yeah. So, yeah, let me remind you. Let me double check it. So, make sure I don't write anything stupid. So, yeah. So the effective aperture, AE, if you remember, so that equals to GR lambda square over 4 pi. Okay, so another 4 pi comes from here.
Right, okay.
Yeah. So by this 4 pi d square, so that's the area of the sphere. Okay. Yeah, so this is called path loss exponent. In practice, this number can be bigger than 2. Okay. Yeah. Normally we denote that as n, right? So for example, if n is bigger than 2, I say if n is 4, right? And so in this case, n is 2, right? But if n is 4, then so this term will become 40 log d. Okay, so you can modify this formula accordingly, depends on the channel property. Okay. Yeah, but in our class, probably we're gonna just use 2. Yeah, but in practice, it could be bigger than 2. Okay, any questions? Okay, great. All right. Okay, so now let's talk a little bit on the path loss more. Okay, so usually in practice, you don't like the definition of the dB. So when we characterize the communication loss, okay, or the received power, we also have some references. Right? Like we denote that as the received power at or loss at d0. Okay. And d0 is some close-in distance. we'll call that relative power and pass loss. Right, so basically we need to, first we have a closed-in distance, d0, okay? So given d0, we could compute the received power at d0, right? Yeah, that is basically equals to, again, so we're going to use that formula, right? So that is nothing but pt times dt times gr lambda squared over 4 pi d squared, right? And d is d0. And now our goal is to characterize PRD as a function of PRD0. Okay, so what are the relationship between these two? Okay, let's compute it, right? So PRD, let's say over PRD0, it's nothing but we can use this formula twice, right? So that's PT, dt, gr, lambda squared over 4 pi d squared divided by pt, gt, gr, lambda squared divided by 4 pi d0 squared. Right, and clearly we can see that. So this term is identical, this term is identical, 4 pi, same, right? So that equals to, we'll have d naught, that will be in the upstairs, right? So those will be the relationship, right? Therefore, we can get PRD equals to d0 over d squared multiplied PRD0. Okay, so that's the relationship. So now, let's say if we know that, then we can get it, right? So those are our reference points. And normally, d0 can be like with a distance of 1 meter. Okay, so now let's express this in terms of dB. Let's say we have PRD in terms of dB. So that is 10 log 10 over this guy, right? PR d0 times d0 over d squared. Okay, so now let's break this too. So we can take this out, right? Break this too. We have, so 10 log 10 of PR d0. So that's basically the definition of the PR d0 in terms of dB, right? So we can write this as PR d0 dB, okay? And then we add 20 log 10 because we take this 2 in the front. And then here we have the 0 over d, okay? Yeah. Then we write this as this minus our PL. So that's the pass loss. Okay, so this is the pass loss. Right, clearly, so the minus of the pass loss equals to this guy, right? So our PL pass loss is dB, so that equals to, so we take the minus inside, so that is equal to 20 log 10 d over d0. Okay, so that's the pass loss. That make sense? Questions? No? Okay, so yeah, let me emphasize one more thing here. So basically, we say a factor of 2 is equal to which dB again? 3 dB, right? Very good. factor of 2 is 3 dB, right? So this basically means that, so every factor of 2 in distance, right, like this. Let's say if we double the distance here, right, and then the loss is the result in an additional, how many dB pass loss? Right, if the distance double, we'll have 3 dB more in distance, and then in terms of for the pass loss, we'll have how many dB more? Remember now it's 30 years 20. Right? So if it's dB, right, if here it's 10, right, if you double the distance, we'll have 3 dB loss, but now it's 20, right, if you double the distance, then we'll have a 6 dB loss, right? That makes sense? Okay, because the distance, is a square relationship. I have 6 dB loss, and let's say if instead of 2, if I have a factor of 10, right, if we increase distance by 10 times, right, and then every factor of 10 in distance, and then how many dB loss we have? 20 dB, right, very good. Okay, very good. Okay, so I have a few minutes. Let me try to give you an example of it. Right, just compute the pass loss a little bit. Let's see. Again, we look at the Voyager 2. It has left the stance goes here. And is approximately 19.5 billion kilometers from Earth. Okay, so now our goal is to find the path loss. Over that distance in dB. Okay. Yeah, for this much distance, so let's see what is the path loss of Voyager 2. How can we do that? Right? The only thing, because we know the distance, right? Basically D equal to this, right? So what we want to use is basically this formula, right? Or this formula. Okay, yeah, this is the path loss. And then we know D, right? Then the only thing we don't know is D naught. Right? What is D naught? Earth. Right? So normally in this case, yeah, it's too short, so we consider D naught as 1 meter. Right? We consider 1 meter like leaving Earth. Right? So that's our reference point. Right? D naught is 0. It is 1. Okay, so now let's compute it. So basically our path loss, dB, is nothing but 20 log 10. And the distance is 19.5 times 10 to the 12 because it's billion. Billion is, the billion 12.
No, but it's kilometers.
Oh, yeah, billion is 9, right? And then kilometer is 9. Very good, thank you. Okay, and then divide that one. Okay, let's compute that. So that is equals to 266 dB. Right, so that's our path loss. Okay, so if you don't, this number kind of still vague for you, so we can convert that to linear. So if it's P out, let's compute what is the linear number here, right? So convert this to linear is 10 to the power 266 divided by 10, so that will give you 3.8 times 10 to the power 26, right? So this is a huge number for pass loss, right? Yeah, we compute that from here, right? We can compute this linear pass loss directly, right? Because that is basically this guy. Okay, so if you compute pass loss, from scratch, so that's 19.5 times 10 to the power 12 directly squared over 1 direct square, right? And then that will give you the same number obviously. Okay, so you can do whatever way that you want. Okay, yep, so we're out of time. So you have one more topic to cover in this domain. It's only like first small topic, so we're going to cover that at the beginning of our lecture. Thank you.